Now we're going to go through the textbook, PowerPoint, whatever, Google Slides presentation for simple linear regression. And I'm going to try to keep this as intelligible as possible because it's the end of the day and I'm feeling it. Managerial, but you just keep going. Managerial decisions often are based on the relationship between two or more variables. And so in that previous video, when we were introducing linear regression, we were looking at the relationship between the size of the college population next to each pizza shop, and pizza shops that are near schools with more students make more money. They have more sales every quarter, right? So this dot right here is a pizza shop, and it's like at 10, 12, 14, 16. It's like 150,000 students go to this, or that'd be 15 times. That'd be 10,000. It'd be 15,000. 15,000 students go to this one right here, and they get 130,000 or 135,000 in sales every quarter. And so, that's showing a relationship between two variables. One is independent, represented by X, and that independent variable is how many students are at the college. And another one is dependent, Y, and that's the quarterly sales. And so, regression, managerial decisions are often based on the relationship between two or more variables, and regression analysis can be used to show how the variables are related. Okay, so if there is connection between them or not. And if you put your pizza parlor near colleges with even more students, do you make even more money? Is there a relationship between that? And so managerial decisions, I'll just also define that. It's just decisions that managers make, managers of pizza parlors and things like that. So often, you're working at a company and they're like, hey, should we put our pizza parlor next to this podunk university? and they only have 42 students? Or should we put it next to, I don't know, Berkeley, and they've got like 60,000 students? Which one should we put it next to? And obviously the one with the more students is going to make more money, but you could show that with regression. The variable being predicted is called the dependent variable, and it's denoted by Y. So the variable being predicted is the dependent variable. It's denoted by Y. And the variable that is being used to predict the value of the dependent variable, the variable or variables being used to predict the value of the dependent variable are called the independent variables, and they are denoted by X. Okay, so that's dependent and independent variables. And simple linear regression involves one independent variable and one dependent variable. So this one would be Y. That's going to be, independent is X, and your dependent is going to be Y. Okay. The relationship between the two variables is approximated by a straight line. So it's simple linear regression and linear. Notice that line is a big part of that word linear. and so here you're looking for the relationship, and it's like, here's the independent variable, here's the dependent variable. I feel like I've said that plenty of times. And the relationship between the two variables is approximated by a straight line. Regression analysis, that's why we use the y equals mx plus b formula. It's a straight line. Regression analysis involving two or more independent variables is called multiple regression, and we're not going to get into that in this class. The equation that describes how y is related to x and an error term is called the regression model. So the regression model, that's the equation that describes how y is related to x, and it has an error term. That's called the regression model. And here it is, okay? And I've also put it right here, just on this sheet. Here's the regression model. That's exactly that same formula. And I just put these all together so you could kind of see how they're connected. And we talked through those in the previous video. And so that's right here. B0 and B1 are called parameters of the model. And E is the random variable called the error term. And then here I put the simple linear regression model. You see model right there. I put that's just from the previous page. But now we're going to talk about the equation. So here's the difference between the model and the equation. So that's what it looks like. And this is just showing, I guess maybe this is the theory, and here is for a population. That's the way I read it. And I have 90% confidence that that's correct. And whenever I do this, I'm like, oh, okay, I got to go check. So I'm going to download that slide. I'm going to come back over here. I'm going to find it. I'm going to upload it from my computer, and that's going to be a download. It's going to be my downloads. And it's going to be that one right there. I'm going to open it, and I'm going to say, is that regression equation for a population. That's how I interpret it after reading about it. Is that a correct interpretation? Whoop. Let's see what ChatGPT says, shall we? Yes, your interpretation is correct. The regression equation shown in your image appears to represent the population regression model. The equation, blah, 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 represents the population linear regression model. Beta naught, oh, cool, is the population y-intercept. Beta 1 is the population slope, the change in y for 1 unit change in x. And epsilon represents the random error term accounting for deviations of the actual values of y from the regression line due to random factors. The equation EY, expected y, equals y-intercept B naught plus B1 slope times x represents, oh, beta 1 is what they call it, not B1, beta, represents the expected value of y for a given x, which also refers to the population regression line showing the average or expected relationship between y and x in the population. So average, right? That's where it is there again. It's, you know, it's not the average of the prices, it's the average of the relationship between y and x. So this equation reflects the relationship between variables in the entire population, whereas the sample regression equation, typically with a small b0 and a small b1, estimates these parameters based on sample data. Perfect. I love it. Really well described. Thank you, ChatGPT. You are amazing. I need to say that. Hold on. Here, I can type fast. Thank you, ChatGPT. You are amazing. Woo. And then whenever you do that, it's like, you're very welcome, Todd. I'm really glad I could help. Your enthusiasm makes my day. Thank you for your kind words. If you have more questions, feel free to ask anytime. It knows my name. It's totally funny. All right, so we have the simple linear regression equation. Here's the model. Here's the equations for a population. And beta naught is the y-intercept of the regression line. And y-intercept, because if x is 0, then where it hits the y-axis, right? When x is 0, it hits the y-axis right here. And so my beta naught would be 60, right? In this example, my beta naught would be, or 60. That's where it looks like it's going in. It looks like it's hitting there. So that's the y-intercept. That's why they call it the y-intercept, because when x is 0, this is all 0. So your y-intercept, your expected value for y, is just going to be that. And beta 1 is the slope. I just have to pause to figure out how to say that. Beta 1 is the slope of the regression line. And EY is the expected value of y for a given value of x. So positive linear relationship. So here's your y-intercept, and your slope B1 is positive. That's the regression line. And a negative linear relationship. So here's your y-intercept at beta naught, and beta 1 is negative. So there's your negative regression line. And then here you have slope beta 1 is 0, and your y-intercept is beta naught. So that's no relationship. So positive, negative, none in terms of relationship. And then, so here we have, just to bring these equations forward, we have our regression model, we have our regression equation, and now we have our estimated simple linear regression equation. So this is the estimate, and it's from a sample, and it's estimating the population. So we have y hat, and we have b0, little b0 plus little b1 times x. And little b0 is the y-intercept of the line, and little b1 is the slope of the line, and y hat is the estimated value of y for a given x value. And it's called the estimated regression line. Okie dokie. And so here's a little diagram of the estimation process. This one kind of confuses me because it's like, where do I begin? But here we have, do I begin here and I keep going around, or do I begin here and keep going around? Here we have our regression model. Here we have our regression equation. Here we have unknown parameters, right? We don't know what this is for the population. Our y-intercept beta naught, or our slope beta 1. So we get some sample data. We do like we get sample data, and we estimate, we have our estimated regression equation, right? Where y hat is equal to that, and we have sample statistics that. And so these are estimates of those. That's what that says. But I'm not sure why we go back up to this. I don't know why that arrow's there. Then we have our least squares criterion. So least squares method. So when, I said, hey, this is how regression works, it's the line that kind of minimizes the distance. It minimizes the SSE. And SSE is the dot, the point, minus that regression line. So this is the regression line, right there. And it's the point. How do we minimize the distance of all these points? What does that line look like passing through all the points? How do we minimize those distances? Again, you have to use calculus to do that. We're not going to use calculus in this course to do it. But here's the idea. You want to do the least squares method. So you take the point and then you minus that point on the expected value of y on the regression line. So yi is the observed value of the dependent variable for the ith observation, and y hat is the estimated value of the dependent variable for the ith observation. And so you would get y hat, that's your regression line. And really, right, like if you just read this, you'd be like, what are they talking about? But when you're like, okay, here are the points, and you're just like finding out the distance, you could do subtraction, the distance from this point to that point, or the distance from this point to that point, or the distance from this point to that point, right? And then you square that so you don't have any negatives. And this is called the ith residual right here, that little portion. And so then you square it so you don't have any negatives. And you sum all that up and you minimize it. And again, that's calculus. But, all the problems we're given, we don't have to do the calculus part. We just have to kind of like, they give us the stuff to plug in, basically. All right, so you minimize it, and then you have the slope for the estimated regression equation. So that's your B1, and I don't know, little b? I don't know if that's what you call it. And I can't click in there to get that one. I don't know why. It's like, oh, there we go. I got it. Boom, get rid of that. So what can we say about this? So we have xi minus x bar, yi minus y bar, xi minus x bar squared. Sum up those, and divide them. And so here we just have, value of the independent variable for the ith observation, x, right? Value of the dependent variable for the ith observation. So you have your x, you have your y. The mean value for the dependent variable, which is x bar, and the mean value for the independent variable. All right, well, if I have a bunch of data, I could calculate all that. I know how to do a mean. I know how to do subtraction. I can multiply these together, add them all up, for each ith variable, and we could do all that math. And I think we'll see that coming up. Well, let's just look right here. So here's this one, right? So here's our x. And like when there's 2,000 students, there's $58,000 worth of sales every quarter. When there's because this is all in thousands. When there's 6,000 students, there's $105,000 worth of sales every quarter. These students love pizza. When there's 22,000 students, there's $149,000 worth of sales every quarter. So we could take xi minus x bar. So here's 2 is our xi, and x bar is 140. Oh, those are totals, and we have 10. So we divide by 10. We get 14 for the mean. So 2 minus 14 is negative 12. 22 minus 14 is 8, right? And then we do that with y. And so again, this is going to be like 58 minus 130 is going to be negative 72. And then we multiply those together, right? Here's that one. And then we also square it. Here's that one. And we get those totals. And so when we do all of that, 2840, and 568, 2840 and 568, right? Here's that equation. We get 5. So our slope is 5, which means that for every increase in one student at a college, because that's our slope, so when x goes over 1, sales go up $5. Right? So for every extra student, every quarter we make that's at a college, we make it $5 at our pizza parlor, which you can see how if you own a pizza shop, that kind of information is going to be useful. And so then we also have the calculation. So that was to calculate this one. And then what else is this one? We haven't seen this one. So the y-intercept for the estimated regression equation is this. Okay? It's that. And you could get to this formula by just going from here, right here, this formula down here. Maybe you can't see it because I'm covering that lower screen. So I'm just going to bring this, I'm going to copy it, and I'm going to bring it up here, and I'm just going to put it like right here. Okay, I'm going to put that right there, and let me see if I can move all this down, which I can. Whoop. Okay, you could pause this video and you could solve right here for B0. You could solve for B0. And if you solve for B0, so basically you're just going to subtract B1x from both sides. And you're going to have y hat minus B1x on this side. And then on this side, you'll have nothing. You have y hat minus bx is equal to B0. Now just flip that around. And you have B0 is equal to y hat minus B1 over x. It's like super close, right? It's like pretty much it's just algebra just to isolate your slope, which is B naught is your slope. And so B naught, that's kind of funny. So you have B naught, and your expected value, also kind of known as the mean of y. If you don't have data, you could just use the mean of y, and minus B1 times x. And so here is the problem the example we've been talking about. And data was collected from a sample of 10 pizza parlors near college campuses for the ith observation or restaurant in the sample, right? Like xi is the size of the student population and yi is quarterly sales. So here's all your data. And then we do those calculations. And then we get the slope. And then we get B0 and And the mean here is 130. And so 130, I think, is the mean that, it's just the average straight up mean right there. And then minus 5 times 14. So 5 is our slope. And then 14, let me figure out, 14 is your x bar. And so that's just going to be 140 divided by 10. Oh, yeah. And then this one is your y-intercepts, 1300 divided by 10 is 130. And so you get 130 right here, which is your y-intercept. And you get your slope, 5, which we calculated right here. And we get 14, which is our x bar, which is 140 divided by 10. And so that becomes, our estimated regression equation becomes y hat. So that's B0, right? That's your y-intercept. I called this y-intercept a second ago. That wasn't it. That was just your mean for y. But then we get this equation here, and we do y hat is equal to the y-intercept, 60. So that's what we were calculating there. Let me highlight that so that stands out to me. And to you, there's your y-intercept, and here is your slope. That's really good to highlight too, because that's what we're doing there. There's your slope, and then here's our estimated regression equation. Okay, so it's an estimate of the population, and it's going to be y hat is equal to 60 plus 5 times x. And now for any x, we could calculate what the sales are going to be for that pizza parlor. And so we could say, hey, there's 1,000 students. So we're going to have 5,000 and revenue of $5,060. Or there's 10,000 students, we're going to have revenue of $50,060. So it's kind of interesting. So that is a simple linear regression. And then here's this equation again, which you could take a gander at, or this page that I put together, where all of those different things are explained. We have the regression model, we have the regression equation, we have estimated regression equation, and I'll make this just a little bit bigger so you can see it. And then we have this regression line right here, y hat, and we have all this stuff. So we've talked about all this. We haven't talked yet about the coefficient of determination or sample correlation coefficient. We're going to talk about those in the next video. See you in the next video.